When we talk about the carbon cycle, we usually think about the fast stuff, trees breathing, oceans absorbing, but there's a much older, slower, and honestly a more epic story happening right under our feet. This is the slow carbon cycle. It's this huge geological drama that moves carbon around over millions of years, and it's basically the master controller for our planet's climate.
So where does carbon go to sleep for millions of years? It's a great question, right? While some carbon is constantly moving through living things, a ton of it gets locked away, put into this kind of deep, long-term storage. So where's that? Well, the answer involves rain, rock, and a whole lot of fire. To really get a handle on this colossal process, let's do something kind of cool. We're going to shrink our focus way down and just follow one single carbon atom. We're going to tag along on its incredible journey across eons, all the way from the sky to the sea, deep into the Earth's crust, and then back out again.
All right, so every great story has a beginning, right? Well, for our little carbon atom, this whole adventure doesn't start on the ground. It begins way up high, in the atmosphere.
And there it is, our hero. Just one carbon atom hanging out with two oxygen atoms, making a CO2 molecule. You can't see it, you can't smell it, but it's there. For now, it's just kind of floating around up there, waiting for the first step of its very long journey to kick off.
Okay, so our atom's first big move, it's not some big, dramatic explosion. It actually starts with something you see all the time, a simple drop of rain. And this is where the real magic, the chemistry, starts to happen.
As rain falls through the sky, it dissolves CO2 from the air, including the molecule with our atom. This creates something called carbonic acid. Now, I know the word acid can sound a little intense, but don't worry, this stuff is super weak. I mean, you'd never even feel it. But, and this is the key, over millions of years, this gentle acid becomes one of the most powerful forces shaping our world. It's wild.
This whole thing is called chemical weathering. So that slightly acidic rain lands on rocks, and it just slowly dissolves them, grain by grain. This reaction frees up all these charged particles, called ions. And yep, our carbon atom is one of them. And where they go? They get washed away into streams and rivers, all headed for one place, the ocean.
So let's recap. Our atom has gone from the air to the land in a raindrop, and now it's just adrift in the vast chemical soup of the ocean. And this is where things get really interesting, because life, actual living creatures, are about to get involved in a big way.
The ocean is just packed with these things called calcifying organisms. It's a fancy term for creatures with a kind of superpower. They can pull dissolved stuff like calcium in our carbon atom right out of the water and use it to build their own houses, their protective shells and skeletons.
And we're talking about all kinds of builders here. You've got everything from microscopic plankton, which are literally the foundation of the marine food web, to the clams and oysters you might recognize, all the way up to the huge, amazing structures that corals build. And boom, this is the next huge leap in our atom's journey. It gets snapped up by one of these organisms and becomes a building block for a brand new shell. So just like that, it's gone from being a free-floating ion in the water to being part of a solid biological structure. Now, the life of that little sea creature might be pretty short, but for our carbon atom, oh, its story is just getting started. It's about to begin the longest, quietest part of its adventure, a sleep that's going to last for millions of years, deep inside solid rock.
After the organism dies, its tiny shell, with our carbon atom locked inside, begins this slow, graceful drift all the way down to the bottom of the ocean. Down and down it goes, joining this massive pile of trillions upon trillions of other shells that have been building up layer by layer for millennia.
Imagine the weight of the entire ocean pressing down. All that pressure squishes these layers of sediment together, burying them, compacting them, and eventually cementing them into rock, specifically limestone. Our carbon atom is now locked away, part of the Earth's crust, where it can stay put for tens or even hundreds of millions of years. But, nothing stays put forever. Not even rock at the bottom of the ocean. The next chapter for our atom is, well, it's the total opposite of a long sleep. It's a fiery, dramatic wake-up call, all thanks to the massive power of plate tectonics. See, the ocean floor is always moving. These giant tectonic plates are shifting around. And in a process called subduction, the plate carrying our limestone gets shoved down deep into the Earth's mantle. And down there, the conditions are just extreme, incredibly hot with crushing pressure. The rock literally starts to cook. As the rock cooks, it transforms, And in the process, our carbon atom gets released again as carbon dioxide. This gas then works its way back to the surface and gets vented out into the atmosphere through volcanoes. That whole release is called outgassing.
And that return to the atmosphere can be super dramatic. Think about a massive explosive eruption, like Mount Pinatubo. It's like a giant geological sneeze, blasting a huge cloud of gas, including tons of CO2, high into the sky all at once.
But it's not always so explosive. It can also be a much calmer, steadier process. Think about the volcanoes in Hawaii, where the lava just kind of flows. They release those same gases, including our carbon atom, back into the atmosphere in a more gradual stream. And just like that, after millions of years, our atom is right back where it started.
So by following this one tiny atom, we've actually uncovered this huge, incredible system, this slow carbon cycle, the pulling of carbon from the air into rock and its fiery return. It's basically Earth's natural thermostat. It's what has regulated our planet's climate over geological time.
It really is this amazing planetary balancing act. On one side, you've got chemical weathering, acting as a carbon sink, pulling CO2 out of the atmosphere. On the other side, you've got volcanic activity acting as a carbon source, putting it back in. And for eons, these two colossal forces have been in this sort of delicate, self-regulating dance. I mean, think about that. This immense, powerful, and unbelievably slow cycle has kept our planet's climate stable for longer than we can really even imagine. Which, of course, brings us to a really crucial question. What happens to that ancient, delicate balance when a totally new and much, much faster force gets thrown into the mix?